today's video, our lesson is all about maxima and minima. And to start, let us consider this remark. To find the absolute extrema, if we say absolute extrema, it refers to the either absolute maximum or absolute minimum. So to find the absolute extrema of a continuous function, say f, on the closed interval from a to b, we follow the following steps. Step 1, we will find the function value at the critical numbers of the function f on the open interval from a to b. Actually, we already discussed this in our previous video. And in the second part, we will evaluate this a in the function and this b as well in the function. And the largest value obtained in step 1 and step 2 is called the absolute maximum, while the smallest or the least value you obtain in step 1 and step 2 is the absolute minimum. So example, a rectangular field having an area of 2,400 square meter is to be closed by fence and then divided into two lots by another fence set parallel to one of the other side. And what must be the dimension of the field if the total amount of fencing material is to be the smallest as possible? So it is obvious here that we are going to minimize. Okay. So let us draw first the problem. So if we are going to draw it, it is a rectangular field, then it will look like this. So it will be a rectangular in form, wherein there will be one more here parallel. So in this case, if this is x, this is also x here. Of course, this is also x because this is a rectangle. And without loss of generality, we assume that this x is less than or equal to your y. By the way, your y is in this side. So we assume that x is less than or equal to your y. And by the way, here, if you look at here, if this is x, this is also x. So it is an obviously formed, we form here an obvious square. And based on the problem, we are given here that the area of the entire rectangle is 2,400 meters squared. So if we are to find the area, x times y, that is 2,400. And if we look at the area of this square, and we know that this is just x squared because this is the square, so you will have your x squared, the area of this square, is just less than the area of the entire rectangle, that is 2,400. So if we will take the square root both sides, it will be x is less than or equal to, it will give us, yes, it is just 20 square root of 6. So the next thing that we will do is we are going to form an equation in the equation that describes the fencing material. So we will define it, we will denote it with f, and we know that there are 3 x's here, so it will be 3x, and there are 2 y's, and it will be 2y. And this is the function that we are going to get the derivative. But obviously, as you observe here, this function involves 2 variables. So we need to do something so that this will only involve either x or y, and we will be using this one. So maybe we will just change this y in terms of x, so y is equal to 2,400 divided by x. So in this case, it becomes 3x plus 2 times our y. And our y is 2,400 over x. And if we will simplify it further, it becomes 3x plus 4,800 all over x. And that is our f. So the next step that we will do is we will find the, okay, by the way, before going through that, well, we will establish first the interval that we have here. By the way, in this case, we know that if x is 0, it will be undefined. You cannot create a rectangle. So here, the interval that we will consider is x is number after 0 and before 20 square root of 6. So we will be using that interval later, the, the 0 to 20 square root of 6. Okay, so let us now take the derivative of this one. So if you get the derivative of the function f, so it becomes 3. So in the technique that we discussed in our previous video, we would just change the sign into its negative. We will multiply the exponent and the numerator. In this case, this is just 1, so you have 4,800 still the same because it's just 1. And you add 1 in the exponent. And that will be the derivative of that function. And again, as we will find the critical value, we will be looking at the portion wherein your function is 0 or undefined. In this case, we will equate it to 0, and we will be solving for x. It becomes 3 equal to 4,800 over x squared. And you can exchange the two. So you have x squared is equal to 4,800 divided by 3. That will just give us 1,600. And if we will solve for x, it will give us 40 plus and minus 40, but we will only get the positive because we are looking for the length. So your x is 40. And this is your critical point, a critical value rather. So we will be solving for the y here. We will go back to the function here. As we will substitute 40 here, you will have 2,400 divided by 40. That would give us 60. So your critical point is the point 40, 60. Okay. So the next thing that we will be doing is we are going to use the first order or the first derivative test. So because that will tell us whether your function is increasing or decreasing into a certain interval. And later also we will be using the second derivative test, testing where is your function is concave up or concave down. So let us continue here. So we will have to use here is the 40. So obviously you have two intervals from negative infinity to 40 and 40 to positive infinity. So if you will get one testing point here, say 41, and if you substitute it here, it will give us, if you substitute it here, it will give us a positive value. Yes, it's a positive. And if you will get a testing point, say 39, so it will give us here a negative value. It means in this interval, your function is decreasing. In this interval from 40 to positive infinity, your function is increasing. Or it somehow, it looks like decreasing, then increasing. So the point 40, 60 is a relative minimum. Okay? So relative mean. So the next thing that we will be doing is we are going to just to assure that we are really sure with our answer, we will be doing the second derivative test, the concavity. Let us see whether it is really concave up to affirm that we really have the relative minimum. So what we will do is to get the derivative of this. So the second derivative of our function f, this becomes 0 because the derivative constant is 0. Change the sign to its opposite, so it becomes positive. You multiply the numerator and the exponent. That's for the technique that we discussed previously. That's 9,600. Then you add 1 in your denominator. And the next thing that we will do is we substitute our critical point here. So if we substitute 40 in our function, it will give us 9,600 all over 40 cubed. And obviously that is greater than 0 or positive. So it is really concave up. So it affirms that this is really a relative minimum. Okay, so the answer in the first derivative and second derivative really coincide. And we will also, based on the theorem that we have, we will also do the second, this one. So let us test whether where is the absolute max and absolute mean. So as you can see, our interval is the half-closed interval from 0 to square root, 20 square root of 6. So if we will consider the interval that we consider in this theorem, so the a that we will be using will not be 0 anymore. So we will start at 1. So in this case, you will have the interval, closed interval from 1 to 20 square root of 6. So we will be evaluating 1 and 20 square root of 6 in the function f. And we know that your f is just equal to 3x, or somehow like, yes, 3x plus 4,800 over x. So if this is 1, it will give us 3 times 1 plus 4,800 over 1. Or somehow, it gives us 4,803. And if we consider the other point, the other number, 20 square root of 6, so we will be substituting that in the x. You will have 3 times 20 square root of 6 plus 4,800 all over 20 square root of 6. That would give us 100 square root of 6. While for the 40 in the critical point that we have a while ago, if we substitute it here, it will give us 3 times 40 plus 4,800 divided by 40, and that would give us 240. So as you can see, the least value that we have here is this one. So it is the absolute minimum. And that is the one that we are looking in the problem, the absolute minimum. So our answer would be this x side should be 40, and the other side is 60. So 40 by 60, that will give us the smallest possible fencing material. So I think that would be all for this video, and see you again for the next video for more problems related to this.